Hi, I'm Chem's best friend. If you like chemistry help, the information how to contact me is on the bottom of your screen. Hello, welcome back. The last video, we went through electron configuration and the periodic table. We discovered how amazing periodic table is, and it actually is a cheat sheet of how to do electron configurations. But there were some exceptions. And we talked about how noble gases don't react because they have s and p orbitals fully filled. So all the other elements want to be like a noble gas. Think about it. If you were little, if you were a girl, did you love playing dress up? I kind of say every girl wants to be a princess, right? So if you cannot be the princess, you will play dress up to at least pretend and act like you're a princess. That's the same thing that elements want to do. They want to gain or lose electrons to have this noble stable gas, to have noble gas electron configuration, and at least pretend to be like a noble gas. So let's go to my screen and continue with our story. So we did our electron configurations, and we learned that there are rules we have to follow when we do electron configurations. We have to fill the lowest energy layer first. That's Aufbau principle. Pauli exclusion says there's 2 electrons per orbital, opposite spins. And Hans' rules say that we have to maximize same spin. And today is the day that Hans' rule day. We will go over this over and over. All right. We also have our chart that you can fill it in. And when we were filling in our electrons, and let's say we did a lot of electron configurations, we learned that there is a pattern, and that everyone here ends with S1, S2, and there is this beautiful pattern. And last video I said, don't worry about this. Well, guess what? Today's the day that we will worry about this. So there is a few exceptions. So there is no D4. This is supposed to be D1, D2, D3. This is supposed to be D4. And then this is supposed to be D5. And yet we see that there's 2 D5s. Oh, and then there's also D5 here. And means 2, 3 D5s. And then we keep going. D6, D7, D8. There's supposed to be D9. There is no D9. And then here's then D10. So this is also D10 and D10. So what's going on? And there's a little bit few other exceptions. We will not get into it. If you are taking AP chemistry class, these are the 4 exceptions you need to know. So here is our exceptions. It's chromium, molybdenum, copper, and silver. Here it is. Here is chromium, molybdenum. Maybe we should make this better visible. So we have our chromium, molybdenum. There you go. And copper and silver. And we can see that they are right on top of one another. Let's figure out why. What's going on? So I'm going to focus on chromium right now. And then you will see what happens in molybdenum. Very, very easy. So chromium, 24 electrons. Let's go back here and do electron configuration for chromium. 24 electrons in a neutral atom. So we're going to fill the electrons. Yes, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. So you would think that it should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. But remember, there's Hans' rule. Hans' rule say you're going to maximize same spin. Hans' rule. We're going to maximize same spin. That also means that half-filled or fully filled orbitals are extra stable. Well, here I am almost half filled. Chromium is almost half filled. Oh my gosh, it only needs one electron. So guess what happens? We're going to, let's color it blue. Actually, let's make it nice pink. We're going to move this electron over here. And here it is. Now, there is no maximize same spin right here. There's only one s orbital. But there is 5d orbitals, and we can have them all with one electron. So half filled will be extra stable. So the correct electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. So this is no. So this one electron goes here. Let's really, so this is 4s1, 3d5. All right. Is this making sense? So this is my exception for chromium. Now what happens with molybdenum? Well, let's do a little bit of erasing so you will quickly see. Let's erase this quickly. For molybdenum, we will have, it's just right below in the periodic table, right? But it's in a 4D level. So we're going to have the same thing, what's happening here, happening right here in this layer right here. Yes, everything that you see here, just move it up. So molybdenum will be the same thing. We can keep going. We can fill it in. I had to erase my 4s. I'm going to fill in 4p, 5s, and then I'm going to go 1, 2, 3, 4. And guess what happens? This one goes over here. Yes. So then molybdenum, I'm going to maybe just a little bit. So MO. Should I do a shortcut way? Why not? Molybdenum, so it's krypton. Yes, krypton. And then I'm going to go to 5s1, 4d5. And let's highlight that. But again, it's s1 and it's d5. So that's molybdenum. So we did this, went here. There we go. Is this making sense? Okay. So same kind of thinking. Let's go to the other exceptions. Remember, we had these two exceptions. We just explained these two. Let's explain copper and silver. And hopefully you can see, oh, I got it. So copper, let's do our electron configuration for copper. In copper, we have 29 electrons, yes, in a neutral atom. Let's fill in quickly our electrons. And the reason I'm not counting is because I'm using my periodic table as my cheat sheet, yes? And I know exactly where I have to stop. I know I have to stop in a 3D region, and I have to fill in 9 electrons in a 3D region. So I don't have to count. Isn't periodic table amazing? It really, really is. Okay, so what we think is that we will have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d9. Yes, 4s2, 3d9. There you go. But Hans rule, maximize same spin. That means half-filled and fully filled orbitals are extra stable. And right here, copper is almost fully filled in the 3D orbitals, almost fully filled. It just needs one more electron. Where will that electron come from? Aha, you know the story now. It comes from 4s. It's going to move in right there. So the electron configuration then for copper will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Let's highlight that. So 4s1, 3d10, right? Not this. So no, this goes here. So this is not correct. And this is the correct electron configuration. Yes? Okay. So we look at our periodic table and we see that silver is right below copper. That means it ends with 4d9. Yes? So the same thing happens here in silver, except in this region, in the 4d region. Right? So I think we can right away write our electron configuration for silver in blue. So for silver, let's do a shortcut way. What will it be? Well, again, we have krypton, and it's going to be 5s1 4d10, because I'm going to just do the same thing. Yes, same thing. It will happen right here if you would like to see it in just a higher region. So I have to go through my 4p, 5s, and then I will have 9, 5, 6, 7, 8, 9, and this one electron will go right here for silver. All right? Is this making sense? So we just explained 4 exceptions that you will be responsible for knowing. And now let's go to some electron configurations of ions. So we notice that metal ions, some of them, yes, we have multiple charges, but right here, the first alkali group and alkaline earth metals, they can only form, +1 or +2 charge. And then right here mostly will be +3, and here is halogens -1, here is -2, -3 ions. So representative elements are pretty straightforward, but then these will be multiple charges, and we're going to deal with this in a second. But, so why do alkali metals, they like to lose that one electron? Yes, because they have one valence electron. There will only be one electron in the outermost energy layer. So how are we going to do this? Well, going just to do, sodium. You look, sodium ion has 10 electrons, and it's going to be just 1s2, 2s2, 2p6, and you're going to lose that. And it was 3s1, and remember we lose that one electron. Yes. So here's sodium. And magnesium. Well, magnesium would like to lose 2 electrons to have electron configuration like neon also. So Mg2 plus, 10 electrons. It's going to be 1s2, 2s2, 2p6. Yes, how do we call that? So these are our isoelectronic series, where you have ions or elements which have a same electron configuration, right? They want to be stable like noble gas. But here, why do some metals have multiple charges? And notice that it's the transition metals that have multiple charges. And then there are some of these, like right here. So I would like to focus on some of them and explain them to you. And the ones that I would like to focus on is, are we ready? I want to explain why is iron +2 and +3. I would like to explain why is copper +1 and +2. And I would like to explain why is tin +2 and +4. And if you know tin, you can know lead. And then, it would be nice to know why is zinc only 2+, why is silver only 1+. There's a little trick right here in the periodic table where you have, aluminum is 3+, zinc can only be 2+, silver can only be 1+. Well, if zinc can only be 2+, cadmium can only be 2+ also. So we're going to go over quickly all of this stuff. So first, let's focus on iron. Why can iron be +2 and +3? Let's go to iron. Iron, all right. Iron, neutral iron, is 26 electrons. So let's fill it in quickly, and then we will see what's happening. We go through 3p, we go through 4s, And then we have 3d6. So 1, 2, 3, 4, 5, 6. Now, I'm going to write my electron configuration for iron. I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Here is the rule for metals. When they lose electrons, you're going to go to the highest energy level by number. So the highest energy level here is 4, right? Because here is 3, 3, 3. The highest energy level is 4. So that means iron will lose these electrons first. All right? So that means that iron, let's maybe do it in blue. So iron 2 plus will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. That's your iron 2 plus. It lost that 4 layer. Okay, now, how can iron be 3 plus? Well, let's think about this. We're going to lose these electrons, so they will be gone. And I look here at my 3d orbitals. And remember Hans' rule? Half-filled and fully filled orbitals are extra stable. So iron is so close right here, the 3d orbitals, to be half-filled. If only we could get rid of that 1 electron, right? So iron 3 plus, what's happening is you're going to remove, let's make this in green, you're going to remove the 4s electron, and then you will remove that 1 from 3d. So iron 3 plus will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5. Is this making sense? So you will notice that most transition metals, because they have that energy layer right here before the D's, can be 2 plus. Most of them, not all of them, but they can be 2 plus right there. So we explained iron. Hopefully it makes sense. All right. Okay, so now let's go to copper. Copper is a little strange. Well, can it be 1 plus and 2 plus? But remember, copper was our exception. So it's easy to explain 2 plus. So let's go to copper. Copper had 29 electrons, and I'm going to fill in 29 electrons really fast to go through this. And again, I'm not counting because I know where I have to end, and I have to do 9. 1, 3, 4, 5, 6, 7, 8, 9. There you go. All right. So I'll have 1s2, 2s2, 2p6, oops, just writing too fast, 3s2, 3p6, 4s2, 3d9. Now, if I actually remember, we go through the highest energy layer right there. If I remove this, I can be copper 2 plus. Copper 2 plus is right there, yes? So we're going to remove these 2 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. But copper 1 plus, remember it was our exception. So we took this electron, we took this electron, we moved it here, right? So copper, the electron configuration actually for copper was, remember, it was 4s1, 3d10, right? And this one was argon. This was electron configuration. So if we remove this one, we remove it, we're going to have copper 1 plus, which is then electron configuration for argon, which is all of this, and then we have 3d10. How is that? So now we know why copper can be 1 plus or 2 plus. Now, hopefully you can see why zinc can only be 2+, and 1 cadmium can only be 2+. Remember, we have our 4s2 3d10. Zinc has 3d10 fully filled. It's not going to touch any electrons in a 3d orbital. So it's going to lose these 2 electrons right there in the 4s region. So zinc will lose that. So if we're going to do quickly zinc, and I'm going to just go, it's argon, and then it's 4s2 3d10. So it's blah blah blah, filled, and right there 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to lose right there these electrons, and it's going to keep everything here. Nothing will change. So zinc can only be 2+, right? And we're going to have argon and 3d10. Now the same story goes with cadmium, 2+. Everything is the same, only 1 energy layer higher. Yes? So cadmium electron configuration, therefore cadmium ion is, well, we're going to go to krypton. And then my 5s2, I'm going to lose the 5s2, and it's going to be 4d10. And this is the reason why zinc can only be 2+ and cadmium can only be 2+. And I would just like to go through one more. So we did these, we did iron, we did copper, we did zinc and cadmium, and you can actually figure out why silver can be 1+. It's that exception with copper. So if you understand why copper can be 1+, you understand why silver can be 1+. But let's go right here. Let's go to tin and antimony. And why I'm going to focus on tin and lead. And I'm just going to focus on tin because then lead will just follow on the higher energy level. So let's go to tin. And I'm just going to really fast erase everything here from zinc. All right. Let's go to tin. Sn. And that's normally 50 electrons. And we're going to fill everything to krypton. And then we have 5s2. Then we have 4d10. And then we have 5p2. Yes, so we're going to, if I'm going to fill it in really fast, this will be filled. I'm going to fill this in, filled, going to fill this in, 6, 7, 8, 9, 10. Okay, so we're going to have our 5s filled. We're going to have 4d filled. And then we're going to have 5p2. All right, so again, electron configuration for ions, cations, you go to the highest energy level. Here it is. And if you're going to have tin 2+, you're going to lose these 2 electrons first. And if you lose these 2 electrons first, you're going to have fully filled D and nicely fully filled S. Yes? So everything will be great. So tin then will be, tin ion will be krypton, 5s2, 4d10. And then tin 4+, well, we're going to lose now these 2 electrons. Yes? So here we go. So we will have just krypton and 4d10. And the same goes with lead, Pb, yes, lead, and it's just in a higher energy level. This will be dealing with, you will have, so like lead, 4+, hopefully you can see it, will be, well, xenon. Oops, I want to squeeze this in, but I don't think I can squeeze it in here. So let's try to squeeze it in right here, maybe in blue. So Pb 4+ will be xenon, right? If I have xenon, I'm going to lose 6s, then I'm going to have 4f14, 5d10, and I'm going to lose the 6p2. Right? So is this making sense? I hope so. So I hope you learned how to do electron configurations of exceptions. Yes, of elements which are the exceptions. You understand why the exceptions, Hund's rule, yes? And hopefully now you also understand why the metal ions, why some of them have multiple charges. Because remember, we're going to remove electrons from the highest energy level first by number, right? And then some of them are these exceptions. So I hope you learned something, and thank you for watching, and see you next time.